The naming and hybridization of the carbons in this benzene derivative. We have a benzene drawing here that is substituted in two positions, one with an hydroxy, one with an amine group. And they are in the ortho relationship to one another because they are right next to each other in a 1-2 position. Now my 3D model here kind of matches the orientation here. Note the differences in geometry and also the similarities. This static two-dimensional image makes everything look flat and not moving. The benzene ring itself is flat, but the hydroxy twists and turns along a sigma bond, and also the NH2 twists and turns. We can get kind of a different thing here. This thing of how these hydrogens are oriented here. Let's name this sucker. Now the largest ring of carbons is the longest strain of carbons is the benzene in the center there. So we're going to start by reading backwards, benzene. And we have the substituents in the 1 and 2 position. We can say 1 and 2 or ortho. I'm just going to say 1, and I'm just going to use the 1 and 2. So in the 1 position, we're going to say 1 hydroxy, 1 hydroxyl, because hydroxy is this OH and YL means it's a substituent. And on the 2, we have amine. So 1 hydroxyl, 2 amine, benzene. A hybridization of these carbons 1 and 2. Just as a note right here, these could have been switched. And as a matter of fact, following like the strict IUPAC rules, I wouldn't be surprised if somebody would say, yeah, they should be switched, because there is an alphabetization rule where, like, if you can list these things in alphabetical order, that's the preferred method. Okay, I'm not going to erase that though. The more important thing is we have the locants 1 and 2 as low as possible. We could have switched these and said this is the 1 and this is the 2, so be very low right here. But absolutely would be a no-no is if we named 1, 2, 3, 4, 5, 6. Naming something 1, 6, not cool. There's nothing else around here. We got to count as low as possible. The hybridization of these 2 carbons. So the first carbon with the hydroxy on there, it is an sp2 hybridized carbon with a trigonal planar geometry. Now the trigonal planar geometry of this carbon is easy to see from the model. How I got there is I counted the number of sigma bonds on this carbon. And this is how I counted the sigma bonds. S, sp1, sp2. My last count of the sigma bond ended in the phrase sp2. So I am determining it is an sp2 hybridized carbon. This right here is a pi bond. I'm not going to count it. I'm counting only the sigma bonds. I'll count again starting from a different location. S, sp1, sp2. Again, I ended on sp2. So I got the sp2 from the count of the sigma bonds around this carbon here. The trigonal planar, that's just something I kind of memorized, how sp2 carbons have this trigonal planar geometry. This second carbon with the amine group on it, let's count it again. S, sp1, sp2. Counting the 3 sigma bonds going around, we get sp2, and again, a trigonal planar geometry around this carbon. Thank you.